When we study the other planets in our galaxy, one of the main aims is to find planets like ours, which support liquid water on the surface and therefore could have the correct conditions for life, just like us. In the last decade, we have launched telescopes, such as the Kepler mission, into space to look for Earth-like planets orbiting neighbouring stars through the unfiltered view of space, and we've found no shortage of these potential Earth analogues. Since the Kepler mission left the blue planet in 2009, we have catalogued, documented and analysed over 4,000 Earth-like exoplanets orbiting stars in the Milky Way galaxy, and as technology marches relentlessly on, we are becoming increasingly capable at detecting planets that have got us excited. However, our estimations are not always bang on, and some of the things we use to infer planetary conditions are not always definitive, and this misjudgment has been epitomised by a recent discovery: the exoplanet K2-18b. A few weeks ago, scientists at University College London published a paper on a new planet which has a mass many times greater than the Earth's, but that likely contains water vapour in its atmosphere among other chemicals and molecules. K2-18b was one of the many exoplanets identified by the Kepler mission, and was discovered around the same time that the star KIC-846 was causing the astronomical community to contemplate the possibility of a super-civilization. K2-18b is located 124 light-years from the Earth in the constellation of Leo. While its diameter is only double that of the Earth's, its mass is estimated to be about 8 times that of our home world. It was originally classified as a Mini-Neptune, a small gas planet with few distinguishable features, especially not habitability. However, scientific analysis over the past 2 years has since suggested that this planet may not be a gas planet after all, and might actually be a type of large rocky planet known as a super-Earth. And a rocky planet is far more intriguing to scientists for what could exist on its surface. In the wake of this revelation, the internet is now awash with speculative stories about the planet, claiming everything from an ocean world to habitable surface conditions for life as we know it. In reality, this seems to be jumping the gun. Like most of the 1,200 planets noted by the K2 Second Light program of the Kepler mission, the mysteries of this planet were not revealed by the automated process of the craft's cataloguing in 2015, but by further examination by scientists. Further studies of the planet using the Hubble Space Telescope have been conducted by researchers at the University of Montreal and University College London, and earlier this year they published their findings to give us our story. In a detailed article in the Nature Astronomy journal, they stated that their findings indicate the presence of water vapour in the planet's atmosphere, and is a major breakthrough for scientists as they aim to hone their biosignature search techniques. This discovery was made through analysing the light reaching Earth from the planet's atmosphere. Spectral data for an exoplanet is collected by waiting for said planet to pass in front of its parent star relative to the Earth. By examining the emission and absorption lines as it passes through the planet's atmospheric layer, the presence of certain molecules can be inferred. For example, a planet with an atmosphere with a high concentration of oxygen will have a thin blue layer, much like the Earth's. Similarly, a celestial object such as Titan, with an atmosphere rich in methane and nitrogen, appears reddish. The spectrum of planets differs based on their atmosphere's composition, and this is a great way for scientists to detect certain familiar molecules, like water, and identify which planets might have similar conditions to the Earth. Water vapour was detected from K2-18b in this manner, and we know that the presence of water is a good starting point for planets where life could emerge. It also just so happens that this planet appears to be orbiting its parent star in its habitable zone, the area which is an optimal distance from its parent star to maintain liquid water on the surface, which is a fundamental building block of life in our world. Neither of these two discoveries conclusively indicate any kind of habitability, life, or even a definitive structure for the planet, but UCL scientists say that it is a good start, and as we improve our planet-determining technology, we may yet be able to analyse the planet in greater detail within the next decade. But regardless of the discovery of water vapour, conversations of habitability and surface conditions are premature, as scientists still cannot yet agree on what the spectral data for K2-18b actually means. Some believe the planet could be a rocky planet with a surface covered in flowing water, whereas others dispute that this planet is even rocky at all. In both cases, however, the discovery of water vapour in the planet's atmosphere would be expected if we were to analyse its atmosphere closely enough. However, this article has become the focus of a number of speculative news stories from some big news outlets too. I myself was surprised to see just how presumptuous the article that the BBC released on the matter was. After reading that and seeing the recent artist's impression of the planet that has swept the internet, You'd be too excited to think that this planet was anything but teeming with life. To the casual observer, any kind of water might give them the impression of an Earth-like planet, but this is far from the truth. As mentioned, the crucial component of the discovery is vapour within the planet's atmosphere, which isn't uncommon among certain types of planets. Vapour in an atmosphere does not guarantee liquid water on the surface, and in fact, you cannot really conclude on anything on its surface. But with that said, we aren't completely in the dark. We can use the Earth as a starting point for our analysis, and we are able to estimate star size and distance through mathematical processes and our knowledge of a star's life cycle fairly accurately. So, when we have an estimation for the size, type and phase of the star, in K2-18b's case a red dwarf, we can then look at how much light is obstructed by the exoplanet in question, as well as the way it orbits its parent star. Once we have an estimation for its size, we can then use the laws of universal gravitation to reverse engineer a planet's mass and weight. This process was followed for K2-18b, and we now know that its mass is about 8 times greater than the Earth's, so we can narrow this planet's type down to the 2 types mentioned at the start, either a super-Earth or a Mini-Neptune. On the one hand, this planet might be an exciting super-Earth. This is a kind of large rocky planet found in some star systems. A super-Earth typically has a much higher mass than the Earth's, between 4 to 8 times respectively, but is less than the mass of the ice giant planets, such as Neptune and Uranus. They form in solar systems where there is much more rocky material available for planetary formation, hence they are able to grow significantly larger than the rocky planets we see in the inner solar system through the process of accretion, the process of dust and rocks smashing together and becoming larger over millions of years as they orbit their parent star. The reason there are no super-Earths in our solar system is because when our solar system was forming, Jupiter had formed very early on, and the godfather planet travelled through the inner solar system, sweeping up much of the rocky material and leaving less for planetary formation. This is also linked to the reason as to why Mars is so much smaller than the Earth. It formed in a region of the solar system where there was far less rocky material available, so for that reason we don't see super-Earths in our solar system. But if we did, there might be less speculation as to what could exist on the surface, because even if K2-18b is a super-Earth as some have been speculating, super-Earths are not generally believed to be habitable due to their mass. Rocky planets this large retain thick envelopes of toxic gases within our atmosphere, not to mention the immense gravitational pressure on the surface. These two factors would create an incredibly inhospitable environment for life to emerge in, and even if simple cellular life could somehow emerge in these dense, silent worlds, complex life forms such as vertebrates would have no chance of evolving under such immense pressure. So even if K2-18b is a super-Earth, its prospects for life are pretty bleak. What's even bleaker, and some way more likely, is that the planet is a Mini-Neptune. A Mini-Neptune, also known as a gas dwarf, is a planet which is up to 10 times the mass of the Earth, but is less massive than the aforementioned ice giants Uranus and Neptune. These planets also have thick atmospheres, which retain high volumes of hydrogen and helium, with deeper layers of ice and rock, and potentially oceans of liquid water and ammonia towards the interior. While we don't know much about these planets, we can use our knowledge of local ice giants to determine some of their broad characteristics. Generally, planets with a radius larger than double the Earth's would be assumed to be gaseous as opposed to rocky, as a planet that size would have a significantly greater mass than the Earth's, and planets larger than 6 times the Earth's mass tend to retain high amounts of hydrogen and helium in their atmospheres, collected during the planet's formation from the leftover gas clouds that formed the system's parent star. On a gaseous planet with such an atmospheric composition, the pressure increases exponentially the deeper down you travel. If K2-18b is indeed a gas dwarf, then its surface temperature could be hotter than 5,000 degrees Kelvin. While we don't fully understand the mechanisms required for life to emerge, complex molecular systems would be required for the very basic life processes, such as replication, to occur. At such high temperatures and under so much pressure, these molecules, which would be essential in forming the building blocks of DNA, amino acids and proteins, are all highly unstable and cannot form, let alone sustain and copy themselves. But on the outer edges of the planet's atmosphere, water vapour could still be detected, but it's improbable that this water could support any form of life. Some also argue that if the planet did have an atmosphere similar to the Earth's, we wouldn't even be able to detect it with current technology. Professor David Charbonneau of the University of Harvard's Astrophysics Division said that the fact we are able to detect this atmosphere is proof in itself that it cannot support life. This impactful yet anticlimactic statement is likely to be true, and it is more than likely that this planet cannot support any form of life, even if we take a very open-minded view as to how life might form. Obviously, the media make their money through speculation and sensationalism. The detection of water vapour to them means life-giving water, and from there they infer all kinds of falsified conditions. Habitable oceans, hospitable climates, you name it. To the average space journalist, any kind of water is enough to peddle a story, but as we see with K2-18b, this simply isn't the case. It isn't necessarily deliberate either. It's easy to see why humanity jumps at the chance to embrace extraterrestrial life at any given opportunity, but the fact of the matter is that science isn't about sensationalism, and the likely explanation is often the most boring. But don't give up hope of habitable water worlds just yet. While K2-18b probably isn't a habitable Earth analogue, that doesn't mean that it hasn't been the focus of some scientific breakthroughs. This is the smallest planet to date that we have ever detected atmospheric features on, and the fact that we are able to detect chemical compositions from planets hundreds of light years away is a very good start. Our world is just the right size to have maintained its magnetic field and protected its oceans, and K2-18b, while much more massive, is only twice as large. As technology is refined, we may yet be able to do the same for smaller planets. Planets of sizes that one would assume are much more likely to be cool, rocky and habitable than the one we have discussed today. The Milky Way is estimated to have over 100 billion planets, and we have barely even begun to scratch the surface of our most neighbouring regions. So even if this one isn't habitable, tomorrow could mark the discovery of something far more familiar.